Hi friends, welcome to my another video. Today in this video, I will discuss about how to select the fuse rating, breaker rating, contactor rating and the overload relay rating for a particular motor. What is the question? The question is we have to calculate the rating for the MCB. We need to calculate the rating of the main contactor of star delta. We need to calculate the rating for the delta contactor. We need to calculate the rating for the star contactor. We need to calculate the rating for a overload relay if there is a particular motor rating available. So this is completely a design topic. Now let us take an example, and with that example we will rate the MCCB, main contactor, delta contactor, star contactor and overload relay rating for a particular motor. What is our example? In our example we have to calculate the size of each part of the star delta starter. For 10 HP motor, 415 volt 3 phase induction motor. Motor efficiency is 80%, motor RPM is 600, power factor is 0.8. Also we need to calculate the size of breaker and overload relay. So question is asking that to calculate the each part of the star delta starter. What is the each part? That is the main contactor, delta contactor and star contactor. Along with that we have to calculate the size of the breaker. What is the breaker size would be for a 10 HP motor, and we need to calculate the overload relay also, overload relay rating also. Here I tabulated all the information from the question. The motor rating is 10 HP. If we will multiply it with the 746, then it will be in the watt. So motor rating in watt is 7460 watt. Motor efficiency as per the question given is 80%. So I tabulated also. This is a 3-phase motor, so the voltage will be 415 volt. The power factor is given in the question 0.8, so I tabulated this one, and it is a 3-phase supply obviously. And we need to calculate the fuse and the breaker rating. Okay, we need to calculate the main contactor, delta contactor and star contactor rating. Apart from that, we have to calculate the overload relay setting. The information for the motor which is given in our example, it's easily available in every motor nameplate. Every motor nameplate will have its rating. Here in our case it's 10 HP. The operating voltage in our case it's a 415. The efficiency of motor in our case it's 80%. The power factor 0.8. So these information you can collect it from the motor nameplate, and after collecting the information from the motor nameplate you can design the MCCB, overload relay, delta contactor, main contactor, star contactor. Before going into the deep calculation to find the rating of MCCB, thermal overload relay, main contactor rating, delta contactor rating, star contactor rating, let us brush up what is delta connection, what is star connection, and what is line current in the delta connection, line voltage in the delta connection, what is line and phase current in the star connection, and what is line and phase voltage in the star connection, because these terms I will use further in my discussion. So as you see that one, for the delta, the line current and phase current is not same, because line current is divided into the two coil current. So the line current and the coil current or the phase current is not same in the delta. The relation is the line current is √3 times of phase current. But you can see here in delta, the line current, the line voltage and the phase voltage is same. So the phase voltage and line voltage is same in the delta connection. Now let us check in the star. In the star you can see that the phase current and the line current is same, but the line voltage is not same as the phase voltage. The relation between the line voltage and phase voltage in star connection is that the line phase voltage is root 3 times of line voltage. Here I given a one simple example. Suppose these are the same motor. In first case, the motor winding is in the star configuration, and the same motor have the second case motor winding is in the delta configuration. Suppose this winding has some resistance, that motor has some resistance, it's drawing a 10 ampere of current. So the line current and the phase current in the star configuration is same, which is 10 ampere, and the line voltage is 400 volt and the phase voltage is 230 volt, which is root 3 time of line voltage. Now come to the same motor when its wiring is configured in delta connection. The line current is 30 ampere, phase current is 17.3 ampere, line and phase voltage is same, which is 400 volt. Here you can notice that the phase current in the star configuration of the motor is 10 ampere. For the same motor, the phase current in the delta configuration is 17.3 ampere. Here you can observe one thing, that the phase current of same motor when it is in the delta configuration is root 3 time of the phase current when that same motor is in star connection, right? Because if we will multiply 10 into root 3, that is 1.732 into 10, then it will come 17.3. Here we can notice one more important point, that the line current is equal to root 3 time of the phase current in the delta configuration. And we can observe one more thing, that the phase current of motor when the motor winding is in the star configuration is 1/3 of the line current. So here I mentioned this, we observe that the phase current in delta configuration is root 3 time of the phase current in star configuration. And second thing we observe, that the line current is equal to root 3 times of phase current of delta configuration. From there also we can derive the value of line current and phase current of star configuration, which will be 1/3 of the phase. This is just an overview. If you need a separate video on this topic, then please write in the comment box. I will make a separate video on star configuration of motor winding and delta configuration of motor winding, and the relation between star and delta configuration. As of now, just remember these three relation, that is the phase current in delta configuration is root 3 time of the phase current in star configuration. Second relation, the line current is equal to 1 by root 3 time of phase current in delta configuration, and the line current is equal to 1 by third time of phase current in star configuration. These three you remember. Now let us move back to our original topic, that is the selection of fuse, breaker, contactors and over relay for a particular motor. To find this, we have to calculate the first full load current for the motor. As per the three-phase power equation, P is equal to root 3 into V into I into cos phi into efficiency. So I will be P divided by root 3 into V into cos phi into efficiency. We know everything. P here is 7460. So I put the value 7460 divided by root 3. V is 415 volt, cos phi is 0.8, efficiency is 0.9. So when we will calculate this, we will get the value 14.4 ampere. So this is the full load current for the motor. The full load current of the motor and the line current will be same. Okay. Now we need to calculate the phase current. As I told you, the phase current is root 3 time of the line current in delta configuration. So I calculated the phase current. 8.32 ampere. Now, as this motor is in star delta configuration, so the starting current will be 3 times of full load current. So it will be 3 times of 14.4 ampere. So it will come 43.2 ampere. I hope you got till here that to find the breaker rating, contactor rating and the fuse rating and overload relay rating, we need to find the full load current of the motor, which is very simple. As per the three-phase power equation, we can get it. The ampere is full load current is 14.4 ampere. The full load current is equal to the line current, and the phase current we will find by dividing the line current by root 3. So we'll get the value 8.3. As the motor is in star delta configuration, so we will multiply it. The starting current will be 3 times of the full load current. So I multiplied it by 3, then we get 43.2 ampere. Now, first we need to select the fuse. There is two types of fuse. Okay, if we are selecting time delay switch, then there is a different calculation, and if we are selecting non-time delay switch, then there is a different calculation. So let us understand first what is time delay switch and time delay fuse, and what is non-time delay fuse. Here you can see that this fuse is non-time delay fuse and this fuse is a time delay fuse. The purpose is same. During overload, the filament will melt and it will break the circuit. But here in non-time delay fuse, due to overcurrent, there will be link will break, and after breaking, this will disconnect the circuit. And during the short circuit, the link will break from 3 portions, so it will reduce the arc inside the fuse after breaking. So this is one time use. Once we use, khalas, this will never be used again. We need to replace it with the another one. Now, time delay switch, a time delay fuse. What is this? There is a spring, there is a solder, there is a link. During the short circuit, this link will melt out and it will disconnect the circuit instantly. It will not take time. But during the overload, what will happen? This solder will melt and it will release the spring. So during solder melting, this will take time in overload time. So it is taking time to melt. Okay, so this is a time delay switch. As per the NEC 43052 standard, if the fuse is time delay type, then the fuse rating will be 300% of full load current. And if the fuse is non-time delay type fuse, then the fuse rating will be 175% of full load current. So as we calculated in our previous step, the full load current is 14.4 ampere for the motor. Okay. Then we will, for time delay fuse rating, 300% of full load current. So it will come 43.2 ampere. And when the fuse is non-time delay type, then the fuse rating will be 175% of full load current. So when we will put this value, we'll get the fuse rating for non-time delay type fuse is 25.2 ampere. So we have to select the nearby value as per the standard selection chart. The nearest available fuse for time delay type fuse is 45 ampere, and for the non-time delay fuse, the nearest standard size available is 30 ampere. Here I want to highlight one more point. This multiplication, that is 300% and 175%, is valid for 3-phase motor. If we have a synchronous motor, then the factor will be different. If it is a wounded type rotor motor, then the factor will be different. Same for the direct current motor, it will be different. So we have to check on for which motor we are selecting the fuse. According to that, we have to find the factor to multiply with the full load current to get the correct value of fuse rating. Hope I'm clear. Now let us move further to calculate the circuit breaker sizing. This is very important. Again, as I told you during the fuse selection that there is two types of fuse, and based on the fuse type there is a different calculation. Same is valid for the circuit size selection also. If the selection of circuit breaker is inverse time circuit breaker, then the calculation will be different. And if the circuit breaker selection will be instantaneous trip circuit breaker type, then the calculation will be different. Before going to the calculation, let us understand what is the difference between the inverse type circuit breaker and the instantaneous trip circuit breaker, and which one should be preferable for the motor, and which one is generally being used in the motor star delta connection. So let us discuss this one. We can say that the overcurrent is happening due to the overload, and the overcurrent is happening due to the short circuit fault. In both the condition, whether the motor get overloaded or whether there is a short circuit in the motor, in both the cases there will be overcurrent, but the severity of overcurrent will be different in both the cases. For the overload condition, the severity of overcurrent is less, and in the short circuit condition, the severity of overcurrent will be very high. In inverse time circuit breaker, there is a thermal magnetic contact. The overcurrent due to overload, this thermal magnetic contact will get heated, and after certain value it will trip the circuit breaker. But same inverse time circuit breaker, during short circuit, this thermal magnetic relay will heat up more fastlier than the overcurrent due to overload condition, so it will trip the circuit breaker more fastly. That's why its name is inverse time, because when the current increase, then when the overcurrent increases more rapidly, then the circuit breaker will trip also more rapidly. So there is a inverse relation between the current and the time. That's why its name is inverse time circuit breaker. So this circuit breaker will provide protection against the overload and against the short circuit. As you will see, there is always an overload relay with the star delta power wiring. We design a circuit, we rated a circuit which will give protection against the overload and against the short circuit fault. Then why we are using overload relay again, if we already provided a overload protection by the circuit breaker? Sometime it will be very difficult, or sometime it become impossible to rate a circuit breaker for a motor which will give both the protection, that is overload protection and the short circuit protection. Why? Let me explain this one. To protect the motor from the overload, we need to select a circuit breaker which will have a rating nearby its full load current, because after the full load current the motor will be overloaded. But suppose this motor have a very high inrush current. Due to this problem, when we select a circuit breaker which will protect the motor from the overload, it will trip unnecessarily due to the high inrush of current. That is why there is always an overload relay with the motor to protect the motor from the overload. The first priority to select a circuit breaker is to protect the motor from the short circuit. And if that circuit breaker is also protecting the overcurrent, then it is well and good. But if that breaker will not protect the motor from the overload, then we will prioritize that circuit breaker selection for the short circuit protection for that motor. As for the overload protection of the motor, there is already an overload relay, so we can size a circuit breaker bit higher, so that even if the circuit breaker not protecting the motor from the overload, it should cover the short circuit fault protection for that motor. As I told you before that the inverse time circuit breaker give protection against the overload as well as against the short circuit fault. But due to the high inrush current problem in the motor, the inverse time circuit breaker sometime and in many time cannot cover the overload protection and the short circuit protection together. In that time, the inverse time circuit breaker will be selected by considering the short circuit fault current of for that motor, because the motor already have a overload relay to protect it from the overload. As sometime the inverse time circuit breaker fail to protect both the fault, that is the overload fault and the short circuit fault together, then we can go only for the instantaneous strip circuit breaker. This will only cover the short circuit fault protection, but it cannot be used alone. It should be used always with the overload relay. So the overload relay will protect the motor from the overload, and the instantaneous strip circuit breaker will trip the circuit and protect the motor from the instantaneous or short circuit fault. As per NEC 43052 standard for circuit breaker selection for 3-phase induction motor, it states that if you are selecting the instantaneous type circuit breaker, then choose the multiple of 800% for the full load current to get the instantaneous strip circuit breaker rating. And if you are selecting the inverse time type circuit breaker for the motor, then use the multiplication of 250% for the full load current for the inverse time circuit breaker rating. So here, suppose if I have chosen the instantaneous strip circuit breaker, then we have to multiply with the 800% of full load current. Our full load current, which we calculated in our previous step, is 14.4. So 800% of 14.4 is 115.2%. So this will be the circuit breaker size. And suppose if I have selected the inverse strip circuit breaker, then as per the standard says that the inverse type circuit breaker rating must be 250 time of full load current, 250% time of full load current. Then it's a simple calculation, then we will get 36 ampere. So when you are selecting the instantaneous strip type circuit breaker, then the rating is 115.2 ampere, and if the circuit breaker is inverse time circuit breaker, then the circuit breaker rating will be 36 ampere. Here I selected an inverse time trip circuit breaker. So my nearest available standard side circuit breaker is 40 ampere. Now let us move further to the sizing of, or to calculating the rating of thermal overload relay. Here we have two cases also. What is that two cases? That if the overload relay is placed in the line and if the overload relay placed in the winding. What does it mean? Let me explain you. In this example, the overload relay is connected directly with the line, okay? But in this example, you can see that this overload relay is not connected directly with the line. It is connected after branching it from delta and from main and from delta's contactor. So due to the placement of the overload relay is different. If the placement is different, then the calculation also will be different. Let us see. And there is advantage and disadvantage for both of the placement of the overload relay, which we will discuss in any other topic. Now let us discuss the first case, when the overload relay is placed in the line. It means I'm talking about this example, when the overload relay is placed in the line, okay? So if the overload relay is placed in the line, then it will supply the entire motors, okay? And it will be, this overload relay will be ahead of where the power is split to the delta and star contactor. So the overload relay size must be based on the full load current. Why full load current? You can see from here, this example, the full load current will pass through this relay. So the sizing or the rating of this overload relay will be based on the full load current of the motor. Okay, so the thermal overload relay setting will be 100% of full load current. What is the full load current? 14.4, which we calculated in previous step. So the 100% of 14.4 is 14.4 ampere. So the nearest overload relay standard size overload relay is 13 to 19 ampere. Now suppose if the overload relay is placed in the winding, meaning this is the case, after branching the overload relay is placed with the main contactor and with the delta contactor. As in the second case, the overload relay is placed after the point where the wiring is split into main and delta contactor, then the overload relay will have only the phase current. And as I explained you before that the phase current is 1 by root 3 time of line current, which is only the 58% of line current or full load current. So the sizing of the overload relay will be based on the phase current, which is 1 by root 3 time of full load current, or we can say that 58% of full load current. 1 by root 3 is equivalent to 58%, means the deduction will be of 42%, so it will be 58%. So 58% of full load current, 58% of 14.4 full load current is equal to 8.35 ampere. So when the contactor is placed after the branching, just after the delta contactor and the main contactor, the relay will be 58% of full load current, that is 8.35 ampere. When the overload relay is placed in the line directly with the line, then the overload relay rating will be 100% of the full load current, that is 14.4 ampere. Now move to next topic, that is the sizing of contactor, sizing of main and delta contactor, sizing of star contactor. To better understand this one, let us go to this slide. Here I explained you that when the motor winding is in the delta configuration, then the phase current is 1 by root 3 time of the line current, and when the motor winding is in the star configuration, then the phase current is equal to 1 by 3 time of line current. So this we will take as a reference to understand this topic. As I told you, when the motor winding is in the delta connection, then it will take 1 by root 3 time of full load current. So the sizing of star contactor, and this will come into the picture only at the starting condition. So I told you that the phase current during star configuration is 1 by 3 time of full load current. So this star contactor dealing with only 1/3 current of full load current. So the rating of star contactor is 33% of full load current, that is 1/3 of full load current. It will be 4.75%. The rating of main contactor, as the main contactor will be active during starting and during the transient time and during the running time, so it will be always active. So during starting it will take 33% of the full load current, but at the transient and at the running time it will take root 1 by root 3 time of the full load current, because it's dealing with the phase current of delta configuration. So 58% of full load current, so full load current is 14.4, so it will come 8.3 ampere. Now let us size the delta contactor. Delta contactor will be active during running condition only, so it will take the phase current of delta configuration winding of motor, which is 1 by root 3 time of full load current, which is equivalent to 58%. 1 by root 3 is equivalent to 0.058, which is equivalent to 58%, okay, of full load current. So full load current is 14.4, so it will come 8.3 ampere. So the star contactor rating is 4.75 ampere main contactor rating is 8.3 ampere and the delta contactor rating is 8.3 ampere. Now the contactor has several types, and based on our application we have to select the proper type of the contactor. Like there is a type AC1, AC2, AC3 and AC4. AC1 is for non-inductive and slightly inductive load. AC2 is slip ring motor. AC3 is a squirrel cage motor, and AC4 is for the rapid start stop motor. In our case, this is induction motor squirrel cage type. All the most of 80% of the motor in the world is squirrel cage induction motor type. Our case also the motor is a squirrel cage motor, so the contactor type will be AC3. So let us summarize this one. As the induction motor is a squirrel cage type, so the type of contactor will be AC3. The nearest available contactor for 4.9 for star calculated rating 4.75 is 4.9 ampere, and for delta and for main contactor 8.3, the nearest standard is 9 ampere for delta and main contactor AC3 type. Now let us summarize all these which we discussed and we calculated. Here at the starting of the video I told you that we need to calculate the rating of MCCB, fuse, thermal overload relay, main contactor, delta contactor and star contactor. So we calculated the fuse 45 ampere, we calculated the MCCB 40 ampere, we calculated the thermal overload relay 13 to 19 ampere, main contactor 9 ampere AC3 type, delta contactor 9 ampere AC3 type and star contactor 4.9 ampere. This is 4.9 ampere, this is 9 ampere, this one also 9 ampere, this one is 13 to 19 ampere and MCCB is 40 ampere, and there is a fuse that will be of 45 ampere. Here the fuse is time delay type fuse and the circuit breaker is inverse time type circuit breaker. Hope you enjoyed my video. If you like my video, please give thumbs up and subscribe to my channel. We will meet in any other video. Till then, keep learning. Bye bye. Thank you so much.